A submarine is a steel cylinder filled with people, equipment, and air. By every intuition, it should float. Steel ships float. Oil tankers float. Aircraft carriers weighing over 100,000 tons float. So how does a submarine, built from the same materials, deliberately sink to hundreds of meters below the surface and then rise back up again? The answer isn't propellers pushing it down. It isn't weights being dropped. It's something far more elegant. Submarines control their depth by controlling their weight, not by adding or removing physical mass, but by replacing air with water and water with air. They make themselves heavier to sink and lighter to rise. This is the engineering behind ballast systems. And once you understand it, you'll see why submarines are some of the most precisely balanced machines ever built. To understand how submarines dive, you need to understand buoyancy. Archimedes figured this out over 2,000 years ago. An object submerged in fluid experiences an upward force equal to the weight of the fluid it displaces. This is the buoyant force. If an object weighs more than the water it displaces, it sinks. If it weighs less than the water it displaces, it floats. If it weighs exactly the same as the water it displaces, it achieves neutral buoyancy, neither rising nor sinking. A submarine operates by shifting between these states. On the surface, a submarine is positively buoyant. It floats like any other ship. The volume of water it displaces weighs more than the submarine itself. The buoyant force exceeds gravity. The boat rides on top of the water. To dive, the submarine must become negatively buoyant. It must weigh more than the water it displaces, so that gravity overcomes the buoyant force. At operating depth, the submarine aims for neutral buoyancy. It weighs exactly as much as the water it displaces. It neither rises nor sinks without active intervention. It hangs suspended in the water column. The mechanism for achieving these state changes is the ballast tank. Submarines have large tanks, typically located between the outer hull and the inner pressure hull, that can be filled with either air or water. These are the main ballast tanks. On the surface, these tanks are full of air. Air is much less dense than water. The total weight of the submarine is relatively low compared to the volume of water it displaces. The boat floats. To dive, the submarine opens flood ports at the bottom of the ballast tanks and vents the air out through valves at the top. Water rushes in, displacing the air. The tanks fill with heavy water instead of light air. Now the total weight of the submarine has increased significantly, perhaps by hundreds of tons, without changing its external volume. It still displaces the same amount of water, but it weighs much more. Gravity wins. The submarine sinks. To surface, the process reverses. Compressed air stored in high-pressure tanks is blown into the ballast tanks, forcing the water out through the flood ports. Air replaces water. The submarine becomes lighter. Buoyancy wins. The submarine rises. This is the fundamental mechanism, controlling weight by controlling the air-water ratio inside the ballast tanks. The numbers involved are substantial. A typical nuclear attack submarine might displace around 7,000 tons when submerged. Its main ballast tanks might hold 200 to 400 tons of water when flooded. That's the weight difference between floating on the surface and being able to submerge. When the submarine wants to dive, it takes on hundreds of tons of water in a matter of minutes. When it wants to surface, it expels that same water using compressed air. The compressed air system is critical. Submarines carry high-pressure air stored in banks of steel flasks, typically at pressures of 200 to 300 bar. This air is compressed using compressors powered by the submarine's main propulsion system. Emergency surfacing, called an emergency blow, uses this high-pressure air directly. Valves open and air blasts into the ballast tanks at tremendous pressure, forcing water out rapidly. The submarine can go from submerged to surfacing in under a minute if necessary. In normal operations, the process is more controlled. Blowing and venting are done gradually to maintain precise control over depth and attitude, but main ballast tanks are only part of the story. Once submerged, submarines don't use main ballast for depth control. The main ballast tanks are either full or empty, nothing in between. They're binary. surface mode or submerged mode. For precise depth control while underwater, submarines use a different system: trim tanks and depth control surfaces. Trim tanks are smaller tanks that can hold varying amounts of water, not just full or empty. By pumping water between trim tanks located at different positions in the submarine, the crew can adjust the boat's balance. If the bow is too heavy, water is pumped from forward trim tanks to aft trim tanks. If the stern is too heavy, the reverse. The submarine maintains level trim while submerged, but trim tanks adjust balance, not overall buoyancy. For fine depth adjustments, submarines rely on hydrodynamic control surfaces, essentially underwater wings. These are called diving planes or hydroplanes. Submarines typically have two sets: bow planes near the front and stern planes at the rear. When the submarine moves forward, water flows over these planes. By angling the planes, the crew can generate upward or downward hydrodynamic forces, similar to how aircraft control surfaces work. To go deeper, the planes angle to push the bow down. To go shallower, they angle to push the bow up. As long as the submarine is moving forward, these control surfaces provide precise depth control. This is why submarines must maintain forward motion to control depth effectively. A stationary submarine has no water flowing over its planes. It can only rely on buoyancy adjustment, which is slower and less precise. There's a crucial difference between buoyancy control and plane control. Buoyancy determines whether the submarine naturally rises or sinks when stationary. Planes determine how the submarine moves through the water when propulsion is active. A well-trimmed submarine at neutral buoyancy can hover motionless at depth. It's perfectly balanced. This is the ideal state for many operations: surveillance, waiting, or conserving power. But achieving perfect neutral buoyancy is challenging because the ocean isn't uniform. Seawater density varies with temperature, salinity, and pressure. Cold water is denser than warm water. Salty water is denser than fresh water. Deep water is slightly more compressed than shallow water. As a submarine moves through different water masses, the buoyant force acting on it changes even though its weight remains constant. The crew must constantly adjust ballast and trim to compensate. This is one of the most demanding aspects of submarine operation. The ocean environment is dynamic. Thermoclines, layers of water with sharp temperature gradients, can cause sudden buoyancy changes. Fresh water from river outflows near coastlines creates density variations. The submarine must respond or risk uncontrolled ascent or descent. Modern submarines have sophisticated systems for monitoring water density and automatically adjusting ballast. But the fundamental challenge remains: maintaining neutral buoyancy in a non-uniform medium. Let me address something that often confuses people: submarines and pressure. As a submarine descends, water pressure increases. At 100 meters depth, the pressure is about 10 atmospheres, 10 times sea level pressure. At 300 meters, it's about 30 atmospheres. This pressure acts on the submarine's hull from all directions, compressing the structure. The pressure hull, the inner cylindrical shell that protects the crew and equipment, is designed to withstand this compression. But here's the key point: pressure doesn't affect buoyancy directly. Buoyancy depends on displaced water weight versus submarine weight. Pressure increases water density slightly at depth, which actually increases the buoyant force marginally. But more significantly, the hull itself compresses slightly under pressure, reducing displaced volume and reducing buoyancy. This means submarines tend to become less buoyant as they go deeper, even without taking on additional water. The hull compression effect works against them. Submarine designers account for this. The trim and ballast systems have capacity to compensate for pressure effects across the operating depth range. Every submarine has a crush depth, the depth at which the pressure hull will structurally fail. This is determined by hull material, diameter, and construction methods. Operational depth limits are set well above crush depth, with substantial safety margin. But the physical reality of increasing pressure constrains how deep submarines can operate. Nuclear submarines typically operate at depths up to 300 to 500 meters. Some specialized submarines can go deeper, The hull engineering required for greater depths becomes increasingly demanding and expensive. The ballast system also plays a role in emergency scenarios. If a submarine loses propulsion at depth, it loses the ability to use control surfaces for depth management. It must rely entirely on buoyancy control. Emergency procedures include blowing all ballast tanks to achieve maximum positive buoyancy. Even without propulsion, this will bring the submarine to the surface. It's uncontrolled and potentially dangerous, but it's survivable. The compressed air reserves for emergency blow are carefully calculated. There must be enough air to empty all main ballast tanks from maximum operating depth, with reserve for contingencies. This emergency system has saved submarines and crews multiple times throughout naval history. When everything else fails, blowing ballast is the last resort. There's an elegant simplicity to the ballast system that's worth appreciating. The fundamental physics is straightforward: weight versus buoyancy. The implementation, while complex in detail, uses basic principles: filling tanks with water to sink, emptying them with compressed air to rise. No exotic technology is required. Submarines operated on these principles in World War I. The ballast tanks on a modern nuclear submarine work essentially the same way as those on submarines built a century ago. What has improved is the precision, automation, and integration. Modern submarines have computer-controlled systems that manage trim and buoyancy automatically, maintaining depth within centimeters without constant crew intervention. But if all electronics failed, the basic manual controls would still work. Open valves, vent air, flood tanks, open high-pressure air, blow tanks, surface. The fundamentals are mechanical and reliable. So to answer the original question, submarines sink and rise by controlling their weight through ballast tanks. Filling tanks with water increases weight. The submarine sinks. Blowing tanks with compressed air decreases weight. The submarine rises. Precise depth control at operating depth uses a combination of trim tanks for balance and control surfaces for hydrodynamic maneuvering. No engines push the submarine up or down. The propulsion system moves the submarine forward. Depth control is a separate function, managed by buoyancy and hydrodynamics. Its physics elegantly applied. The same principle Archimedes understood in his bathtub, scaled up to control a 7,000-ton machine beneath the ocean. There's actually a similar principle used in aviation, though most people don't realize it. Aircraft also use weight distribution and trim systems to manage balance, and fuel can be transferred between tanks to adjust the center of gravity during flight. I've explained how that works in another video.